If your Kc is a large number, then you're going to favor products. You're going to have more products than reactants. If your Kc is a very small number, then you're going to have a very small amount of products compared to your number of reactants. All right, so far when we were determining which direction the reaction would go, we had a zero. You can't have a zero at equilibrium, so it would go to the side that had a zero to reach the equilibrium. Now we're going to be given some problems where you have concentrations of both reactants and products, and you'll have to determine which direction the reaction goes. And you will do that by comparing that with your Kc. Note that your expression is exactly the same, but Kc is at equilibrium, and the Q, and you can put QC if you want, the Q is not at equilibrium. So it's the same expression, but the numbers you're putting in are initial or any situation that is not equilibrium. When you're putting in your equilibrium concentrations, then you have Kc. The expression is exactly the same. All right, so if you had this reaction that we had before and we showed the expression for Kc, the expression is exactly the same. C raised to its coefficient, capital D raised to its coefficient, capital A raised to its coefficient, capital B raised to its coefficient. Products over reactants. Now they're putting a little I here saying that it's not at equilibrium, and so it is your initial concentration or any non-equilibrium condition. But your expression is exactly the same if it is a Kc, except all those letters are E because they are at equilibrium. All right, so here are the three situations when you calculate your QC. So Kc is a equilibrium constant at a given temperature. All right, and so you're going to then calculate the QC. If you look at the two numbers, if you see that your Kc is much larger than your QC, so your QC is too small. All right, and again, it is your products over reactants. All right, so you have calculated what you have right now, which is QC, which would be initial usually. You give an initial, you find the QC, you compare it to the Kc. If you find that this number is too small, and you do that by seeing that it is much smaller than your Kc. So if your Kc is much larger than your QC, Q has to get bigger, so it is eventually going to reach equilibrium. In order for this number to get bigger, we need more products. In order to get more products, the reaction has to go to the right. All right, and so anytime your Kc is larger than your QC, the reaction will go to the right to make more products. The number is too small. To make the number larger, we need more products, less reactants, and then eventually you will reach that value of Kc, which at that point, your rate of forward and reverse would be exactly the same, and you would not change any more concentrations. Another choice would be that your Q value is way too big. So you calculate a Q and it is way bigger than your Kc. So if your QC is much larger than your equilibrium, that means it has to get smaller because it's going to eventually get to the Kc equilibrium constant. And so for that number to get smaller to reach the Kc, that means we have to get rid of products and get some reactants. So anytime your Kc is too large, you have too many products. So it has to go to the left to get rid of some of those products. And then the last choice, which is rare when you're given this question, but it can happen. They can give you what they will call initial concentrations, but then you calculate it and it's exactly the same as the K value. So they didn't give you initial concentrations. They gave you the equilibrium concentrations. So if you calculate your QC and it's exactly the same as Kc, then you are at equilibrium. All right, so you will be given concentrations of products and reactants. You will then compare it to the equilibrium constant, and then you will see which way the reaction is going to go. All right, so when we are calculating equilibrium concentrations, we're going to do this in a couple of different ways. The first way is very simple. You're going to be given everything except for one unknown, and then you simply solve for that one unknown and you get your answer. So if you have every other concentration but one and you're given Kc, you can solve for that missing concentration. We will do an example of that. The other choice is when you have a Kc and the initial concentrations. Then you have initial concentrations of Kc. You got to find the equilibrium concentration. So there are three ways that we're going to do this. And so the first way is that when you set it up, you will see that you have a perfect square. And then you will take the square root of both sides and solve that algebra equation simply by doing the same thing to both sides. Nothing special to solve it. Very easy algebra. However, when the Kc expression is not a perfect square, then you have to use the quadratic equation to solve it. Or, I guess it should be still part of B, or successive approximations. And that is if Kc is small. All right, so it has to be pretty small, like 10 to the minus 4, and then successive approximations work much better. If it is not small, then you will have to use the quadratic equation or do 20 to 30 successive approximations, which is not easier. So we will go through all of those ways to solve for a concentration. All right, so here is our reaction. And again, the equilibrium's not coming in, it's coming in as a rectangle. Those are the equilibrium arrows. All right, and so the first thing you want to look at when you have a reaction is to make sure that there are no liquids or solids that you are eliminating in your expression. All of these are gases. Always want to look for that. All right, a gaseous mixture contains 0.3 moles of CO, 0.1 mole of H2, and 0.02 moles of H2O, plus an unknown amount of CH4 in each liter. This mixture is at equilibrium at 1200 Kelvin. All right, so the question is, what is the concentration of CH4 in this mixture? And then they give you the equilibrium constant, and that is 3.92. All right, so the first thing you want to do is write the expression. Kc is concentration of products, CH4, raised to its coefficient 1, H2O raised to its coefficient 1, divided by CO raised to its coefficient of 1, and hydrogen raised to its coefficient of 3. All right, and so they are all gases. They all go into your equilibrium expression. All right, so now we see, if we want to do initial here, all right, they don't give us an initial. So they're saying this is at equilibrium. So they don't give us the initial. They give us this at equilibrium. So they go right to equilibrium. So you have to read the question. Many times they're saying you're starting with this. This question says the mixture is at equilibrium. And so at equilibrium, we have 0.3. 0.3 molar of CO, that is moles per liter. Hydrogen, we have 0.1 mole per liter. CH4, that is the unknown. That's what we are solving for. And then water is 0.02. And that's at equilibrium. And so now we just plug in our numbers. Kc is given, 3.92. The concentration of CH4 at equilibrium, that is what we are solving for. The concentration of water at equilibrium, 0.02. The concentration of CO at equilibrium, 0.3. The concentration of H2 at equilibrium, 0.1. And here's where you will find most errors, because people forget. They'll write the 3 here, but when they put the number in, they won't put the raised to the third. That is the most common error of, you know, you got it right, but you forgot something and now you got it wrong. Make sure that anytime it is squared, raised to the third, that you do that function on your calculator to get the right answer. So we take our 3.92, and then we're going to multiply both sides by 0.3, and then we're going to multiply both sides by 0.1 to the third, and then we're going to divide both sides by 0.02. And then we have our answer for CH4. That is 0.59. And that is molar. Make sure you put your units with your number. Yeah, I thought there was a 0 in there. My calculator didn't. So 3.92 times 0.3 times 0.1 to the third divided by 0.02, and that is 0.059. So that's 0.059 molar. Not sure what happened on that one, but all right. So you just plug those in and you have your answer. All right. So here we have another rectangle, which indicates that that is at equilibrium. All right, so the following reaction is used to increase the ratio of hydrogen and senseless gas. If you start with 1 mole each of carbon monoxide and water in a 50-liter vessel, and so to get the molarity, you take 1 divided by 50, and that gives you 0.02. So you have 0.02, and there was 3 sig figs, so 0.0200 molar of CO, and 0.0200 molar of H2O. All right, it didn't say anything about CO2, didn't say anything about hydrogen, and those are zeros. Again, it says if you start, okay? So this is not at equilibrium you have, this is if you start, and so this is initial. All right, so then you have zeros. You cannot have zeros, so the reaction has to go to the right to form some product. At equilibrium, you cannot have a 0 concentration. It has to be a positive concentration. All right, so you have minus your coefficient x, minus your coefficient of 1x, plus your coefficient of 1x, plus your coefficient of 1x. And so at equilibrium, you have 0.0200 minus x, you have 0.0200 minus x, you have x, and you have x. All right, and so then you write your expression. So your expression for Kc is your concentration of CO2, concentration of H2, everything here is a gas, everything's going in there, concentration of CO, concentration of H2O, products over reactants, and everything there is a gas, they all go into the Kc. All right, so they give us the Kc, it's 0.58, and so we have 0.58, now we're plugging in our numbers, is equal to CO2 at equilibrium is X. Hydrogen at equilibrium is also X. Your CO at equilibrium is 0.0200 minus X. Your H2O at equilibrium is also 0.0200 minus X. All right, so now we have a perfect square. To show that, we will rewrite it. We have a 0.58. And on the numerator, we have x times x, which is x squared. in the denominator, we have 0.0200 minus x times 0.0200 minus x, which is 0.0200 minus x quantity squared. And so now we have a perfect square. In the numerator, we have x squared. In the denominator, we have 0.02 minus x squared. And so to solve when you have a perfect square is to take the square root of both sides. So on your calculator, you take the square root of 0.58, and that gives you 0.76. And then the square root of x squared is simply x. The square root of 0.02 minus x squared is 0.0200 minus x. And now we solve for x. And so we have to multiply both sides by 0.0200 minus x. Multiply both sides by 0.0200 minus x. All right, so it's gone on this side. All right, so times 0.02. So that is 0.015 minus 0.76x is equal to x. Then we're going to add 0.76x to both sides. And then we get 0.015 is equal to 1.76x. And then finally, we have to divide both sides by 1.76. And we get 0.0057. Sorry, 0.0087. And that is in moles per liter. All right, so that is your x value in moles per liter. All right, except the question is how many moles of each substance are in the equilibrium mixture? Well, the volume is 50 liters. So to get that to moles, we have to multiply that by the 50 liters so that the liters will cancel. So when you multiply it by 50, you get 0.43 moles. All right, so if the question was, a lot of times the question is, what is the final concentrations? Then you have your 0.0087, and you have your 0.0087 for your equilibrium concentrations. And then for this, you have your 0.02 minus 0.0087. So that is 0.0113. Molar. So you take your 0.0113 times 50, and you get 0.57. All right, and so this is equal to 0.57 moles. All right, so the CO, what you're going to be at equilibrium, is 0.57 moles. Same with your H2O, 0.57 moles. And both the CO2 and the H2 are the 0.43 moles. All right, so they will walk you through all those steps as well. All right, so step one, starting concentrations. They gave you moles, they gave you volume. You convert it to molarity because in your KC setup, the units must be in moles per liter. All right, and then of course they didn't give you any concentrations for the products. They are both 0. All right, and so you set up your equation here, your initial, I call it initial, they call it starting. All right, I do ICE, initial change equilibrium. All right, so just like we had it before, 0.02 for both of the reactants, 0 for both of the products. Has to go to the right. Every coefficient is a 1, and that's why it is minus 1x plus 1x plus 1x, because the coefficients are all 1. And so at equilibrium, we have our 0.0200 minus x, or 0.0200 minus x, and then we have our 0 plus x, which is x, 0 plus x, which is x. So that's what we have at equilibrium. Then you put it into your expression, so you will write your expression, and then you will put in your equilibrium values. All right, and so your CO2 and your H2 were both x, your CO and your H2O were both 0.0200 minus x. Then we combine them to show a perfect square. All right, and so then we were able to take the square root of both sides because we show that this one has a perfect square. And when you did that, again, when you take the square root, you get a plus or minus answer. You can ignore all minus answers. You can never have a negative concentration. You can never have a negative mass. So you eliminate the negative answer. And so you use the positive answer. It is impossible to get a negative concentration. So anytime you solve it and get a negative concentration, that is the invalid answer than the other answer. So even quadratic will give you 2. It's the plus or minus b squared minus 4ac. The positive answer is the only correct solution for these types of problems when you're doing concentrations. All right, and so that was in molarity. All right, so then you take your 0.008 6, I got 8.7. It was 8.65, so it depends on sig figs. Again, if your number is different here or here, that's where the error's at, and that is the correct answer. All right, but at the end, they get the 0.57 and the 0.43, which is what the question says. What are the moles? 0.57 and 0.43. All right, so when the KC expression is not a perfect square, then we're going to use the quadratic equation. So you've got to put your math into the form of x squared plus x plus a constant equals 0. And that gives you your A, it gives you your B, and it gives you your C. And so when you're solving for x using the quadratic equation, you have to have the negative b plus or minus the square root of b squared minus 4ac all over 2a. Again, you have a plus and a minus. The minus answer, if you get a negative value for x, that is an invalid answer. You can never have a negative concentration. So you're only going to have one correct answer when doing the quadratic. You'll always get 2 numbers. One is an invalid answer, and the other one is the answer. All right, so here we have our equilibrium. All right, and so we have 1 mole of hydrogen, 2 moles of iodine. They are placed in a 1 liter vessel. All right, and so when we do our initial, and then we do our change, and then we do our equilibrium. All right, so our initial concentration of hydrogen is 1 mole per liter. So it is a 1 mole per liter. The iodine is 2 moles per liter. So that is 2 moles per liter. All right, and so that's what was placed into the flask. It doesn't say anything about HI. which means that they didn't put any in. So if they put some HI in, it would be stated that they added some amount of HI. If it doesn't say that, then they didn't put any in, and it is 0. So that tells us that the reaction must go to the right. You can never have a 0. And so you have a minus the coefficient of 1x. You have minus the coefficient of 1x. You have plus the coefficient of 2x. Make sure you're looking at your coefficients. All right, so at equilibrium, we have 1 minus x. We have 2 minus x. And we have 2x. All right, and then the Kc at this temperature, again, this is at 458 degrees Celsius. If you change the temperature, you will change the equilibrium constant. All right, and so it is given Kc for this reaction is 49.7. All right, so then you always would put your expression. All right, and so your Kc is your HI squared, because it is raised to the coefficient of 2. And in the denominator is your hydrogen and your iodine. All right, and so then you put in your equilibrium numbers. All right, so Kc is 49.7. The concentration of HI at equilibrium is 2x. The concentration of H2 at equilibrium is 1 minus x. The concentration of I2 at equilibrium is 2 minus x. All right, and so this is going to be an assignment for you. I want you to solve this and bring it in tomorrow on a piece of paper. I will then go through it at that time, but I want to give you a chance to do this by the quadratic equation. So solve by quadratic. So that is your x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So you have to rearrange this into your ax squared plus bx plus c is equal to 0. So you've got to rearrange this, you got to FOIL that, you've got to multiply it, you got to subtract things, and then you have to put it into the a, b, and c. Ax squared plus bx plus c is equal to 0. Plug in your a, b's, and c's, get your two values for x. Only the one that is a positive can be the correct answer. You can never have a negative number. If both answers are positive, if one of the answers is positive and greater than 1, then you would have 1 minus a number greater than 1, which would give you a negative answer for the final concentration of hydrogen. So sometimes they give you two positive numbers, which would work on the HI side, but it will not work on the other side. So if one of the positive numbers is greater than 1, and you say 1 minus x, and you say the final concentration of hydrogen is negative something, that is impossible. And so you're only going to have one valid solution. You're going to have two values. Only one will be a valid solution. So I'm going to let you try to solve that, and then we will do that in class tomorrow. Do not look at their answer. Do it yourself and see what you get. You can compare it to their answer after you do it, but you should do that on your own first. All right. Le Chatelier's principle. This is going to be very important. You have a system at equilibrium, and you're going to make a change. So it's perfectly where it wants to be. The rate of the forward is the rate of the reverse. Then you're going to change something like the temperature, the pressure, and the concentration. And then you're going to have to then predict, is that change going to make it go to make more products to the right, make more reactants to the left, or is it not going to change anything? Is it going to still remain at equilibrium? And so there will be a number of these questions on the test. So these are very important to understand why the reaction will shift the way it does. All right, so first one we're going to do is add more reactant. All right, so we can add more reactant, or we can add some product, or we can remove some reactant, or we can remove some product. All right, so when you have your reaction, you have your reactants going to products. And we are at the perfect equilibrium. So we are at equilibrium. We have the perfect amount of reactants, the perfect amount of products. Rate of the forward is equal to rate of the reverse. And now we're going to add more reactants. If we add more reactants, now we have too many reactants. We had the perfect amount of reactants. Now we added more. Now we have too many reactants. That means that the equilibrium has to shift to the right. It has to go to the right to get rid of some of your excess reactants until that ratio is back to its equilibrium. So anytime you add a reactant, the equilibrium will go to the right, to the forward direction. All right. Now, if you remove your product, all right, so we had the perfect amount of product, and now we're taking product out. Now we don't have enough product. So again, it has to shift to the right, the forward direction, to make more products. We had the perfect amount, we took it out, now we don't have enough. It has to go to the right to form some more. All right. So if we added product, so we're at the perfect amount of product. We add product. Now we have too much product. You have to go to the left to get rid of some of that product. All right. So anytime you add a product, it is going to shift to the left. If you are going to remove reactant, that's the last one. All right, we have the perfect amount of reactants. We take it out. We do not have enough reactants. It has to shift to the left to make more reactants. So the reaction will proceed to the left to make more reactants in order to reach that ratio of products to reactants for your equilibrium constant. So you need to know what happens to the equilibrium when you add or subtract reactants and products. All right, so here is a equilibrium. Predict the direction of the reaction when H2 is removed from the mixture. All right, so we are at perfect equilibrium. We have the perfect amount of H2, and now we're going to take some out. Now we don't have enough H2. The reaction has to proceed to the left to form more of the H2. So again, we had the perfect amount of H2. It says now we're going to remove the H2. Now we don't have enough. It has to go to the left to form more hydrogen. All right, so that's what happens when we change our concentrations. So make sure you know what happens when we change our concentrations. One other thing over here, if you're changing a liquid, if you're adding more liquid, if you're adding more solid, that is not going to have any effect on the equilibrium. If it's not part of the expression, it will have zero effect on the equilibrium. All right, so if you're adding some more platinum solid, and what is the effect? They will have zero effect on your equilibrium. All right, if it's H2O liquid that you're adding more of, it will have zero effect on the equilibrium. All right, so pressures. So now when we have gaseous reactants, all right, so when we're doing pressures, we're talking about gases. All right, so we're going to change the pressure. All right, so if you look at a piston, if it's inside the piston and we want to increase the pressure, we just push down on the piston. All right, so that would increase the pressure. All right, notice that an increase in pressure is a decrease in volume. All right, so when you increase the pressure, you're smashing it down and the volume is decreased. So the rule is if the pressure is increased, all right, so if the pressure is increased, and that will be decreasing the volume, you increase the pressure, you're decreasing the volume of a reaction mixture. the reaction will shift in the direction of the fewer moles of gas. All right, so you have less room, you're going to go to the side that has fewer moles of gas. All right, if your balanced reaction has the same number of moles of gas on both sides, the equilibrium is unaffected. All right, so this is where you can increase the pressure and it will have zero effect on the equilibrium. If you have the same number of moles of gas on both sides of your reaction, it would have zero effect on the equilibrium. All right, so if I go back, let's go back to this one. So if we increase the pressure of this, we have 2 moles of gas on the left side, we have 2 moles of gas on the right side. If you increase the pressure here, it would have zero effect on the equilibrium. You have 2 moles of gas on both sides of that reaction. All right, now here we do not have the same number of moles of gas on both sides of this equilibrium. We have 2 moles of gas on the left, and we have 2 plus 1, 3 moles of gas. Remember, that's how we also calculate our delta N when we are converting Kc to Kp. That is the moles of gaseous products, 3, minus the moles of gaseous reactants, which is 2. And so your delta N is 1. If your delta N is 0, then changing the pressure will have zero effect. If your delta N is not 0, it will definitely have an effect. All right, so here we have the reaction, and we're going to increase the pressure. All right, so when we increase the pressure, we decrease the volume. It's going to go to the side with the fewer number of moles of gas, which is this side. And so it is going to proceed to the left until it reestablishes equilibrium. All right, so if you increase the pressure here by decreasing the volume, this is going to make the reaction go to the left, which means you're going to have fewer amount of products. Products are reacting to give more reactants. And so this will lower the amount of products that are being formed. So anytime you increase the pressure, the equilibrium will shift to the side with the fewer number of moles of gas. All right, so what would you expect to be the effect of an increase in pressure on each of the following reactions? All right, so here is again that rectangle is an equilibrium arrow. All right, so the first thing you have to do is see that you can calculate your delta N. Gaseous products, 3 moles of gaseous products. Gaseous reactants, 3 moles of gaseous reactants. And so since you have 3 moles of gas on the reactant side and 3 moles of gas on the product side, there is zero effect when you increase the pressure. All right, so here is an example that you have to look for the phases. So if you're going too fast, you would say there's 2 moles on this side and 2 moles on that side. And what you just said is not wrong, but your answer is going to be wrong because you were not complete in your answer. There's 1 mole of gas and 1 mole of solid and 2 moles of gas. When we're doing pressure, we only care about the moles of gas. When we're doing delta N, we only care about the moles of gas. All right. The solid is not part of your equilibrium. If you are giving your expression for Kc, it is your concentration of CO squared divided by the concentration of CO2. The solid carbon is not part of that equilibrium. All right. And so when you're calculating your delta N here, you have 2 moles of gaseous products, you have 1 mole of gaseous reactants, and so it is not 0. Your delta N is 1. So when you increase the pressure, it is going to go to the left because the left side only has 1 mole of gas, whereas the right side has 2 moles of gas. So when you increase the pressure, decrease the volume, you're going to go to the side with the fewer moles of gas. Another question here would be, what is the effect on the equilibrium if you add more carbon? So if you see that as adding a reactant, you're going to get the wrong answer. adding more carbon, which is a solid, has zero effect. It is not part of the equilibrium. All right, so that would have zero effect on the equilibrium if you added some solid. All right, but when you increase the pressure, it is going to go to the left because the left side only has 1 mole of gas, or versus the right side with 2 moles of gas. All right, we can also change our temperature. When we change our temperature, we will have a change in our equilibrium. Remember that your equilibrium constant is constant at a given temperature. If you change the temperature, you change the equilibrium constant Kc. All right, so note, we're going to do this on Thursday, and we will find when we increase our temperature, this reaction that we're doing in the lab is going to go much faster. So reaction rates increase with increase in temperature. So this is a fact. It doesn't matter what kind of reaction. You're going to increase the temperature. You're going to increase the rate of that reaction. Now, when we change the temperature, it's going to change the value of our equilibrium constant. It's going to cause a shift in the equilibrium. The direction of these changes, so the shift of the equilibrium, whether it's going to give more products or more reactants, is dependent on the sign of your delta H. All right, so you're either going to have an endothermic or an exothermic reaction. All right, so if you are given a positive delta H, so if your delta H is positive, then you have an endothermic reaction, and that means that heat is a reactant. So for endothermic reactions, where you have reactants going to products, heat is a reactant. When you are exothermic and your delta H is negative and you have your reaction, now heat is released. Heat is a product. So when we look at the heat, as we increase the temperature, we increase the heat. So if you have an endothermic reaction and you increase the temperature, which will increase the heat, which is going to increase the amount of reactants, the reaction is going to go to the right because we have too much heat to get rid of some of that heat. All right, and so that would then shift it to the right. If you did the same thing on an exothermic, you increase the heat by increasing the temperature. So you increase the heat by increasing the temperature of the reaction. Now you have too much heat, and it's going to go to the left to get rid of some of that heat. All right, so you have to know what effect you're going to have for an endothermic and an exothermic. You look at endothermic, heat is a reactant. Exothermic, heat is a product. All right, so carbon monoxide is formed when carbon dioxide reacts with solid carbon graphite. All right, note here that solid carbon has nothing to do with our equilibrium. They give us the delta H, and that value is positive. And so we know that we have heat as a reactant. All right, and we know that because of the positive endothermic delta H that is given right here. So that is positive. That is endothermic. Heat is a reactant. All right. And so if we want this reaction to go to the right, to form more carbon monoxide, if we added more heat, then we would have too much heat, too many reactants. It would shift it to the right. And so in order for this to give more product, more carbon monoxide, we want a high temperature. And that will make the reaction get rid of some of that heat by going to the right, forming more CO2. All right, so then the next question would be, do you want a high or low pressure? All right, we still want to form, we want the reaction to go to the right. We want to form as much carbon monoxide as possible in this reaction. All right, so the question then, high or low temperature, we want a high temperature because it's endothermic, and if we increase the temperature, it makes the reaction go to the right. All right, now when we're looking at high or low pressure, we see that we have 2 moles of gas on the right. We have 1 mole of gas on the left. If we increase the pressure, it's going to go to the left. We don't want to increase the pressure. We want it to be a very low pressure. When it is a very low pressure, that means it is a large volume. It's going to go to the side with the more moles of gas. And so if you wanted this reaction to give as much product as possible, you would run it at a high temperature and a low pressure. All right, so optimum conditions for reactions. All right, low temperature is going to favor high yields if a reaction is exothermic. All right, so if you want the product to go to the right and it's exothermic, you want low temperatures. All right, if we're doing the Haber process and we are making ammonia, here are the optimum temperature choices. Note that for all reaction, if you want it to go faster, you want a higher temperature. However, with this reaction, if you have a high temperature, you're going to have a lower yield of ammonia because you increase the yield of ammonia at a lower temperature. All right, and so that means that this reaction is exothermic. And so you have your choice. Do you want the reaction to go fast, or do you want to have more of your product at the end? All right, so no matter what reaction you're going to do, if you increase the temperature, you're going to increase the rate of the reaction. You may actually lower the yield because if it's exothermic, a high temperature is going to lower the amount of product that you get. And then remember, a catalyst only changes your energy of activation. All right, you start and end at the same spot. The catalyst is just going to lower your energy of activation. Concentration of products, concentration of reactants are unchanged. So you add a catalyst, it has zero effect on the equilibrium. It gets to equilibrium faster, but if it's at equilibrium, it doesn't do a single thing. It just gets there faster. All right, and that is the end of chapter 14. Tomorrow we're going to go through that quadratic equation problem, and then we will go on to chapter 15. Next week, we will then review for the test on next Thursday. I'm planning to make a video on how to fill out your report sheet and posting that to Moodle. I think you fixed the microphone. All right.
These are first, but you probably said what how to do
Did you show the work for this one?
For these ones, yes.
Yeah. So
I just didn't know what
we don't know what this is, but we know what that is. So
Okay.
if you plug that number in here, you get this number.
Okay.
So that's all you're doing. You have this number, you're plugging it in here, and you're finding that number.
Okay, for both, even when it says undiluted or diluted.
No, the diluted is what you get. That's diluted means lower concentration. Undiluted means what came out of the bottle. So we took this out of the bottle, but after we mixed it, it's that concentration.
Okay.
So when we're calculating this concentration. And then to get back to this concentration, we just plug it in right there, and then we get back to that concentration.
Okay, got it.
So the answer that you're getting is this one, and I'm asking undiluted, like what came out of the bottle.
Okay, undiluted out of the bottle.
Yeah.
Got it.
Diluted means after you added the 3 and 5, the 5 and 5. That's
yes.
Diluted. Undiluted is the 5 that just came out.
Got it. Okay.
Yeah. Yep.
For